Hello, welcome back. So, we already looked at sketching, and one thing you might have noticed is that there are certain graphs which maybe cross the x-axis, there are certain graphs which just touch the x-axis, or there are certain graphs which don't touch the x-axis at all, right? So, that's what we're gonna look into. Now, let's take an example. Let's say y equals let's say 2x plus 1 whole squared plus, let's say, 1. Right, so right off the bat I can see that my quadratic will look something like this. Right, I know that it will be a quadratic such that it's all above the x-axis, as in it doesn't touch the x-axis at all. Right, so what I'm gonna do is I'm first gonna expand this. So 2x squared plus 4x plus 3, this will what will come out to be. But what if you look at the quadratic formula and you wonder, well, if we do minus b plus minus square root of 4 square root of b square minus 4ac over 2a, this is the quadratic formula. We know that the quadratic formula gives us the roots. That is, if I equate this to 0, this formula should give me the values of x which satisfy this equation. Right, but we know that, well, from what we can see, this quadratic is all above the x-axis. It is never 0. So what happens to the formula? Let's try it out for ourselves. So minus b plus minus square root of b square minus 4ac over 2a. Right, so minus 4 plus minus, well, 64 minus this should be 16, 4 squared. Right, so 16 minus 24 is minus 8 over 4. And so here is where our problem lies, a negative square root. Right, so a negative square root is sort of a problem for real numbers. Right, if I take minus 2 squared, it gives me 4. If I take 2 squared, it also gives me 4. And hence we conclude that square root of 4 is plus or minus 2. That is, if there's a number, when we square it, it gives me 4, that number is either plus 2 or minus 2. But the problem is that there is no real number that when I multiply it by itself, it will give me a negative number, because positive multiplied with a positive gives me positive, negative multiplied with a negative gives me multiplied with a negative gives me positive, right? So as far as the numbers that we are concerned with, this does not work, this breaks down. And so this square root part, that was the b square minus 4ac part, is what determines it all. So in this case, for this quadratic, my b square minus 4ac was a negative number. And so we can see that if my b square minus 4ac is a negative number, then that quadratic does not touch the x-axis. So the quadratic will be either all above the x-axis or it will be all below the x-axis. And this b square minus 4ac is something that we call the discriminant. Right, and so if discriminant is less than 0, the quadratic does not touch the x-axis. Now let's take a look at a situation where it does cross the x-axis at two different points. Let's say this is minus 2, this is plus 2. So our quadratic can be this thing, which is basically x squared minus 4. If we try to apply our formula here, well, minus b plus or minus square root of b square minus 4 ac over 2a, we get 4 times 4, negative 4 times negative 4 is 16, square root that will be 4 over 2. Okay, so we get plus minus 4 over 2, and so we get our x equals 2 or x equals negative 2. We get our roots. Right, so when the discriminant is positive or greater than 0, there are two distinct roots, two distinct real roots. Alright, here when it is less than 0, there are no real roots, right? Remembering that roots are just the points where it intersects the x-axis. Alright, so we talked about when discriminant is less than 0, we talked about when it's greater than 0, but what about when it's equal to 0? Right, so if I take let's say x minus 3 whole square, I know that x minus 3 whole square looks something like this, right? This is 3 comma 0. It is a quadratic such that, well, it doesn't intersect the x-axis at two distinct points, but it isn't also all above or all below the x-axis. It just touches it at one point. So when d is equal to 0, the roots are what we say they're real and repeated, right? If you want to think about it this way, that there is just one root, there's, well, it's the right way of thinking, but just for the sake of being correct, we say that the roots are real and repeated, because there's an important theorem that for any quadratic there must be two roots. Anyway, so x minus 3 whole square, let's expand this. X square minus 6x plus 9, and if we try to find out its roots, let's say we try our discriminant. So discriminant will be b square minus 4ac, which in this case is 36, minus 4 times 9, which is 0. So when our d is 0, the roots are the quadratic just touches the x-axis, right? Because the quadratic formula is minus b plus or minus square root of the discriminant over 2a. So when my d was negative, this was a problem, that we got a negative root. We got a negative root, and that was a problem. If my d was positive, well, one of the root was this, the other root was this, right? So we had two real and distinct roots. When d is equal to 0, then we just have b plus or minus square root of 0 over 2a. So we just have minus b over 2a. Alright. So this was in the perspective of a single quadratic, when you're sketching it or when you want to have some idea of it. There's another use of it. Let's say there's some quadratic, let's take the same quadratic, x minus 3 whole square, and let's say there's some line 2x plus k. So if I were to plot this, this will look something like this. This is my x minus 3 whole square, and my 2x plus k, where the k is unknown. It could be anything. It could be something like this or this or this or this or anything. We don't know. What if I ask you, find the values of k for which this line does not intersect the curve, does not intersect the curve. Right, so if I have a line like this, it does not intersect the curve. What are the range of values of k for which this is true? So what we will do is, we will first equate the two y's. So x minus 3 whole square is equal to 2x plus k. A square minus 2ab plus b square is equal to 2x plus k. X square minus 8x plus 9 minus k is equal to 0. Now, if I have any quadratic, ax square plus bx plus c equals 0, if my discriminant is negative, we discussed how there will be no real solution to this. If my discriminant is greater than 0, we discussed how there will be two distinct real solutions to this. We discussed how if d is equal to 0, how there will be one solution to this, and it will be like two repeated solutions. So what I want here, I want this equality to never hold. I want this curve to never be equal to this line. So what I will do is, I will take the discriminant and I will find the values of k for which the discriminant is negative. Right, so minus b square minus 4ac is less than 0. 64 minus 64 plus 4k is less than 0. K is less than 0. Right, so for any value of k less than 0, my line, my 2x plus k line will all be over here. They will never intersect the curve, right? Let's take another case. Let's say find the values of k for which it intersects the curve at two distinct points, right? So anything like this, these are my two distinct points, anything like this. But it must not just touch the curve, it must not just intersect at one point. All right, so this is the case of d being positive, right? When d is positive, we have two solutions. So what we will do is we'll take the same d and we will set it to greater than 0. So we get the same thing, that 64 minus 64 plus 4k is greater than 0. And so for any value of k that is greater than 0, we will have the line will intersect the curve at two distinct points. Alright, and of course similarly, if I set my d equal to 0, it will give me that exact value of k for which it just touches the curve, right? That is k equals to 0. Now the last case that I will look at is finding the values of k for which the line meets the curve. Right, so when we say meet, what we really mean is the same thing as, okay, it can intersect at two different points, but it can also be the case that it just touches the curve. It just touches the curve over here. So there's too many lines. When we say that a line meets the curve, it can be anything like this, that it intersects the curve at 2 points, or it could also just touch the curve at one single point. Right, so notice how this is just the combination of these two cases. So what we can do is we can set d equal to greater than and equal to 0. And so this will give us 64 minus 64 plus 4k is greater than equal to 0. K is greater than equal to 0, and this is our answer. Alright, so this was discriminants.